Hi everybody. So this is the second video on modeling mixtures with first order differential equations. In the first video, I showed you how to set up a model and then to solve it using the integrating factor method. If you watched that video, do you want to give this question a go yourself? You can download the worksheet from my website and then pause the video and come back when you've given it a go. Okay, so welcome back if you had a go. So we're told that two liquids, oil and water, are being mixed in a tank, and the mixture is stirred constantly so that each liquid is evenly distributed. Initially, the tank holds 15 litres of oil and 15 litres of water. We have our inflow and our outflow, and we're told to let X be the amount of oil in litres in the tank at time t seconds after the change begins. We need to set up the differential equation and work out beta. So the rate of change of the amount of oil will be dx by dt. And this will be the difference between the rate at which the oil comes in, this is our inflow, and the rate at which it leaves. This will be our outflow. So our inflow, we're told that oil is added at 1.5 litres every second. So this will be our inflow. Our outflow will be the 2.5 litres per second multiplied by the concentration of oil in the tank. So this will be X over the 30 litres. We know it's 30 litres because the inflow is equal to the outflow. So dx by dt will be the 1.5 minus 2.5x over 30. And this is x over 12. So you can see that beta will equal 12. Okay? So that's our differential equation. So to solve this, we need to use the integrating factor method. So we need the x terms on the left-hand side. So we've got dx by dt, 1 over 12, multiplied by x, will be 1.5. So we'll use this negative 112 for our integrating factor. And this will become e to the 1/12 of t. And then we'll multiply every term in this differential equation by this integrating factor. So when you differentiate the left-hand side with respect to t, we get this right-hand side. And then if we integrate both sides with respect to t, these will cancel, and we'll work out the integral of this right-hand side. And when you integrate e to the 1/12 t, we can use the reverse chain rule. So we'll multiply the 1.5 by 12, and we'll get 18. And we need to add in that constant term of integration. So using the initial conditions, when t equals 0, we know x will equal 15. When you substitute in the 0 into here, we get 1. So this will just become 15. When we substitute the 0 into the right-hand side, this will become 1. So we'll have 18 plus c. Therefore, c will equal -3. And then we can substitute this constant back into our equation here. And then to make x the subject, we'll divide both sides by the exponential term. These two will cancel, and we'll have a negative power with this 3. So now we've got our model for how the amount of oil in the tank changes with respect to time. For part B, work out the concentration of oil in the liquid for large values of t. So if t tends to infinity, then this term will tend to 0, because we'll have -3 divided by this very large number. So if this bit becomes 0, then the amount of oil will tend to 18. And the concentration will be the 18 litres over the constant 30 multiplied by 100 to find out the percentage, this will be 60%. So for very large values of T, the concentration of oil in the tank will be 60%, okay?